Thank you for inviting me here. I'm actually very happy to be in Minnesota. I grew up in Sweden, and this is the first time I've come to Minnesota, and I had the chance to explore the state a little bit this weekend, and I realized that everything is the same as in Scandinavia here. It's like the rock is the same, the trees are the same, and so I went up to Lake Superior. Even the waves move the same way as it does in Scandinavia. Anyway, my wife asked me why I put this picture of a boat here, and my answer was because I just like it. But the reason it's here is to point out to those people who don't know where the Naval Research Laboratory is. So that's in Washington, D.C., which is nearby the Chesapeake Bay. It's a place I like a lot, and try to spend as much time there as possible. All right, so, and this is Thomas Edison. So he was the one who recommended that the Naval Research Laboratory is founded. All right, so modeling into the materials, that's a very broad topic, so I had to really select something. So I've done research on graphene, I've done on transition metal dichalcogenides. So in this particular talk, I'm just going to focus on one area, and in this case, graphene. So I'm going to start with some motivation and give you an idea of where we are going with the graphene work. Then I'm going to talk some general about graphene theory, so I think that's appropriate for a summer school. I'm going to talk about graphene line defects. So this is a microscopic structure that has been observed in graphene, and it has some extraordinary properties that's really brought out because it sits at the intersection of 1D and 2D. Some general modeling of barriers in graphene, and then I'm going to talk about something that we patented recently, a graphene resonant tunneling transistor. So graphene has many exceptional properties, and we all know them. Many of them have been discussed today already. The one that I'm particularly interested in for this talk is the mean-free path. We know that the mean-free path can be very long in graphene, and we know that even from the days of carbon nanotubes, where you could have ballistic transport over long distances. However, in graphene, so here's a band structure. The Fermi level sits right here, and you have these points where things come down. So there's really no band gap in this structure. Of course, everyone wants to see applications, but we don't have a band gap. So how do we switch devices? And I refer to this as the switching challenge. So one way to create a band gap in graphene is to make graphene nanoribbons. Now, people have looked at ribbons for a long time. Actually, we call them strips first, graphene nanostrips. So if you actually search on nanostrips, you probably find a lot of the work we did about 10 years ago. The reason we call them strips was because of this work by Douglas Klein. He called them graphitic polymer strips. So we just followed that. And I think a lot of other people called it ribbons because that's what Fujita called them. Now, I thought that this was the original work. A lot of people thought of this. Now, this outdates that. But then I realized later on that, well, if you really go back, there's work in the 80s on the nanoribbon. So this is published in Japan back in '87. So already then, they could see that the band gap depends on the width of the ribbon with and it oscillates. So that has been apparently known for a very long time. Now, people started to do first principles calculations of these structures in 2006 and thereafter. So this is work by Stephen Louie, where they see the three families. Now, what was surprising is that they all have a band gap. from the nanotubes, we expected that 2/3 would be semiconducting and 1/3 metallic. But that's not the case. So in fact, when Louis and colleagues published this work, we had actually already done our own DFT calculations. And we also saw that there was this gap in all nanoribbons. However, we didn't really understand what was going on. So we actually didn't publish that at the time because we had no idea what was happening here. So Louis, they claimed that it had to do with edge distortion that creates this gap here. However, when we made our calculations, we hadn't relaxed the structure at all. We actually just used idealized coordinates in our DFT calculation. So we knew that edge distortion had nothing to do with it, at least in the results we saw. And eventually we figured out what the reason for it. And the reason is that there are longer range interactions in graphene. Usually you can ignore them. The second nearest neighbor, they couple the same sublattice, so it doesn't really couple the two sublattices. The third nearest neighbor, however, actually turns out to have exactly the same symmetry as the first nearest neighbor. So the third nearest neighbor usually just renormalizes into the first nearest neighbor, and you never see it because you just use an effective nearest neighbor model. But what you don't realize is that you're actually including these longer range interactions inside your hopping parameter. Well, the second you make nanoribbons and you create edges, you break the symmetry between the first and the third nearest neighbor. And that's the reason you create this gap, or at least the dominant reason. And I shouldn't say that edge distortion isn't also happening. Both effects are actually happening, and they reinforce each other. But the main reason is this third nearest neighbor interaction. All right, so something else we did early on, we looked at what happens when you have edges and disorder along the edges, because that was really the difference between graphene nanoribbons and carbon nanotubes. Carbon nanotubes are seamless in a way. They don't have edges. But these ribbons have edges. So we really wanted to know what is the effect. And to our disappointment, we realized that the edges actually have a significant effect, a very strong effect. So what's happening is that these edges cause strong Anderson localization. So we were the first to point out these things back in early 2007. And subsequently, we calculated the scaling of the localization length. And one of the things you see is that the localization length, that's really a measure of the distance where you could have transport before it localizes. Well, it turns out that this localization length scales with the width squared. This scaling is different from disorder. So Enrique just talked about the disorder in graphene. Well, the localization length just scale with the width generally. So because we have these two different scaling effects, this actually explains the very simple question: how come it is difficult to measure narrow ribbons? Philip Kim realized that in 2007 already, that when you make these narrow ribbons, in fact, he suggested that if you make them narrower than about 50 nanometers, he actually thought that his ribbons broke. But that's not the case at all. What's happening is that you create strong localization, so he actually doesn't see the transport when you make two narrow ribbons. Well, of course, in wide graphene, like say a few hundred nanometers wide or a micron wide, you have edges there too. How come it's not creating a problem there? Well, it is again the scaling. So there's actually a crossover where the regular scattering starts to dominate the edge scattering, and that crossover is somewhere between 15 and 40 nanometers, depending on the edges and the direction of it. So this is really the explanation why it's so difficult to get good transport properties in narrow ribbons. So just to give you an example here, if you have 1 micron long ribbon and assume that your the ribbon is 100 nanometer wide, the localization length is of order 6 microns. So that's much longer than the length, so that means that you could have good transport. Now, on the other hand, if you have a narrow ribbon, the localization length is just much shorter than the length of the ribbon, so you get localization. And really, the way we see localization is through variable range hopping. All right, so I, in some sense, want to redefine the gap. The challenge now is that we have no gap, so the challenge is how do we create a gap without strong localization? So this is the old approach. You want to have a ribbon, but edge roughness creates a problem. However, that's not the end of the story, because this work actually stimulated a lot of research around the world. So people started to unfold ribbons. They started to look at nanocutting, and even better, they started to grow nanoribbons using precursors and in polymer form, and create ribbons that way, and they have perfect edges. So there's a lot of research going on graphene nanoribbons still. Now the alternative approach that I'm going to talk about here is that how about having transport across a confined region? This way we can in some sense probe the confinement, but since the transport is going this direction as opposed to along the confinement, we are not sensitive to the edge roughness. This is a way of having a cake and eating it too. So some people might say that, well, there's nothing really new here. People try to create PNP junctions before, where you have some electrostatic gate and you try to dope a central region. All you're doing then is that you're trying to create a confinement. However, that doesn't produce any good results, and the reason for that is that you have Klein tunneling. There's other effects that were reported, like the Veselago lensing. People also saw resonant tunneling. Now this is actually, they assumed that there was a mass already in graphene, so they assumed that there was a gap, which is not the case, so it's a bit of a hypothetical. But anyway, the point here is that all of this comes from a prediction in 1998 by Ando, who talked about the absence of backscattering. So that's essentially saying that if you have slowly varying potentials, then normal incident carriers are just not having any backscattering. Now, this here doesn't look like a slowly varying potential, and this is a little bit confusing to a lot of people, because this happens to be an extreme case where if you draw them perfectly straight up and you don't change the material, so this is a hypothetical, you actually happen to not cause any scattering here. So Katznelson completely ignored scattering at the interfaces here, and it just happened to work out in such a way that you can describe Klein tunneling here. But I think in practical experiments, Klein tunneling is really about slowly varying potentials. All right, so what's the difference here? The problem is slowly varying potentials. If, on the other hand, we can get short-range scatterers, the situation is very different. Over the last 5 years or so, more and more work has been published on grain boundaries and also on this line defect in graphene. So these are two examples where you have short-range scatterers. And once you have short-range scatters, you have normal scattering. I'm going to focus really on this line defect because this has some really interesting symmetry, and it's perfectly straight and it's stable. It actually preserves the sp2 hybridization in graphene. So each carbon site here has 3 nearest neighbors, and it's perfectly flat. So it just, all one has really done is that you can almost view it as you have cut the graphene and then separated a little bit and then inserted some atoms or removed some atoms. And what makes this really exciting now is that just a couple of years ago, they have shown that these line defects can be controllably grown. So just to give you an idea of what I'm looking at here, and I'll return to this in more detail later. What you see here is graphene. I assume that we have a scatter here and another scatter here, creating a confinement, and I do calculations on this. Calculations where I assume that the transport goes from a source contact over to a drain contact. So these are just quantum transport calculations. And what you see is a significant gap. And this may not surprise you. This gap turns out to be very similar to the gap you would have in a corresponding nanoribbon inside its confinement. So this gap is actually not a true band gap, but a transport gap. And it depends on the width, width of this confinement. So this is a new concept that we actually just recently patented. Now the line defect also has a lot of other interesting properties following from the symmetry. One of them is that it allows for value polarization, and I'll talk more about that in detail here shortly. Also, there is a possibility for ferromagnetism and a 1D switchable ferromagnet. So this is also something that's very exciting, and it really originates from the localized states around this line defect that show up right at the Fermi level. So you can actually easily lower the band energy of this system by breaking the symmetry in some way. And one of those ways is to create a local magnetic moment. And by symmetry, these moments actually must be aligned. So the short-range order is ferromagnetically aligned. And this is a big improvement over nanoribbons. Zigzag nanoribbons have been predicted to have magnetic edges, but the ribbon as a whole is expected to have antiferromagnetic coupling across a ribbon, so you don't get any net magnetism. Here you would just get a net magnetic moment. There's also the potential for chemistry, and these line defects are actually very reactive, at least that's what we expect, because it contains these 2 carbon atoms here underneath, and you can easily envision any diatomic molecule just wanted to come down and sit right there. The binding energy actually is very strong, and I'll talk more about that later. All right, so that's the general introduction here. So now I'm going to take a step back and just talk about some of the basic theory in graphene. So I know this is a summer school, so we should just look at some of the basic theory here. And I hope this actually complements a little bit of what you just heard from Enrique earlier. Enrico. So one of the models that has been used in graphene for a very long time, actually since 1947, is the tight binding model. So in graphene, you can just write down the tight binding model. Graphene has translation symmetry you can use, and you can calculate the Hamiltonian in K-space, and from that to get the energy dispersion. So the energy dispersion in graphene looks like this. And a lot of people ask me about, well, there are 6 corners, so it looks like there are a lot of values, but there aren't really 6 values, there are really only 2 values. And the way to see that is to actually use a different reciprocal primitive cell. So the first brilliant zone is shown right here with the gold hexagon. But that's not the only choice you can make of a reciprocal primitive cell. There are many other representations, such as this green rectangle here. And these contain exactly the same states as are contained in here. So now if I plot the band structure using this primitive cell, this is what you see. And now you see 2 clear Dirac cones and the 2 values that these Dirac cones represent. So the values here are blue and gold. Navy colors, if anyone is wondered. All right, so some basic valid properties here. Usually when we do calculations on graphene, we aren't really concerned about the value. If you do transport calculations, typically you multiply your result by 2 to reflect that there are 2 Dirac cones, and that's usually the only thing we do, and then we're happy. But there is more to it. So the reason we usually ignore it is that the 2 values are completely degenerate in energy. And the reason for that is that there is a symmetry line in graphene. So if I just consider reflection around this line here, you see the graphene structure is just mapped onto itself. Now in reciprocal space, what you do when you do this reflection is that you actually map one valley onto the other valley. And that just immediately implies that the 2 values must be degenerate in energy. Now that is just the energetic part. However, each quantum state, I mean, there's a state associated with, so that's just the energy. The state itself is not the same in the 2 values. And the way to see that is to center the wave vector around the 2 values. So tau now is plus minus 1, and it represents the 2 values. If you do that, so this is the wave vector to find a particular valley. The phase factor contains these 3 phases. It's really 0, 108, and plus minus 120 degrees. So if you just plot the phases in graphene, so they're color-coded here, you see that in the 2 valleys, they're actually opposite of each other. So if you try to perform any reflection here, you just you don't map it onto itself. So the states are really different. And that's how we can get a valley polarization, by distinguishing the valley eigenstates. So, and why are we interested in valley? Well, it's just another degree of freedom, just like spin. And we know that it's robust against slowly varying potentials, and it can represent binary data. So let me then continue. Something else that's very common. A lot of people start from a Dirac model. And the way to get there, you can get there from the tight binding model. And I appreciate it, thank you. So the way to do that is just to expand the wave vector around the 2 Dirac points. So if you do that and just use the linear order of the dispersion, you just find the following Hamiltonian, where sigma x and sigma y are Pauli matrices. And this is a Fermi velocity, which is related to the nearest neighbor tight binding hopping. So maybe a lot of people here have done this exercise already, but if you haven't, I really recommend it for everyone. Well, if you do it, you wouldn't be first. This was also done a long time ago, by the way. So a lot of the theory was done way before we caught up with experiments. So anyway, so what we have here is a linear dispersion now describing the states around the Fermi level. A lot of people use this representation because it is really you can obtain the Dirac Hamiltonian through a unitary transformation. So this is actually a very, thank you so much. This is a very convenient representation. We won't use that here, and the reason we won't use that here is because it's actually hiding some of the physics if you do that. So we just use the, the Hamiltonian that we derived up here. All right, so continuing. So if you assume that you have this Hamiltonian, we can also now calculate the carrier group velocity, which is just the derivative of the dispersion with respect to the with a wave vector. And what we find is that the velocity of the carriers is aligned with the wave vector q. Now this is a wave vector away from either of the two values. So it's a wave vector measured from this point, not from the gamma point. Well, because of this relation, you can actually also describe the wave vector as a function of q, which is a function of energy, and alpha, which is now the direction that we're traveling. And this relationship is actually very important because all of a sudden you can now think in terms of what are the carriers doing, what direction are they traveling. So we're going to look at scattering here in a minute, and this scattering is having a certain direction. You can specify that with the alpha. So the eigenstates of graphene can be written on the following form, where theta is a pseudospin angle. But then again, there's a relationship now between the pseudospin angle and the valley information and the direction of the carriers. So you can actually rewrite the carrier eigenstates here as a function of valley and the direction. All right, so and what we show here is just a direction of the pseudospin. And what you see here is that this is a pseudospin in one valley, the blue here, and this is a pseudospin in the other valley. And the q is the direction the particle is moving. So now you immediately see that they aren't necessarily aligned. They're only aligned when you do a unitary transformation to obtain the Dirac cone. I'm sorry, to the Dirac Hamiltonian. But generally, it looks like this, and this is just obtained from the tight binding. But it's very important, this distinction that the pseudospin is not necessarily aligned with Q is actually what allows the valley polarization to happen. So I mentioned this line defect before. So assume that you have a line defect now in the vertical direction, and assume that you have a carrier coming into this line defect and scatter. So it can either go through or it can be reflected back. So what is shown here is the transmission probability. The gold is perfect transmission. The deep navy blue is the no transmission. So as you see, the transmission depends on the angle of incidence. And this we have just obtained from quantum transport calculations. You can call it non-equilibrium Green's functions, or you can call it Kudu formalism, or you can call it any other name as you want. Actually, many of these quantum transport techniques are really just the same formalism expressed in different ways. So this shows the transport in one valley, and this shows in the other valley. So for a given alpha, in one valley you can have transmission go through while it's reflected in the other. Well, we can actually calculate this analytically as well. You take the quantum transport calculations and you just start to approximate the energy around the Fermi level. And you find the self-energy for graphene, a broadening matrix. So those of you who have done quantum transport, you're probably familiar with this. You can also obtain a Green's function. This is a Green's function on the line defect, which is described by this Hamiltonian. And you can calculate the transmission probability in a given valley using this expression right here. And you get a nice compact result of the transmission through the line defect. Well, this is all with the quantum transport formalism. You can actually obtain it just by using some rudimentary physics, and that's what I'm going to show here. It's all nice that we can do fancy calculations, but if you really understand the physics, that's even better, at least in my opinion. So the assumption here is that we're going to take a limit where the wave vector goes to 0. So that means that the state we're approaching the Dirac cones, right the center of the Dirac cones. Well, in that very limit, you actually have a strange case where the translation operator commutes with a reflection operator. This is usually never the case, but in this exact limit, you actually have this satisfied. Well, when that is the case, you can form symmetry adapted states that are simultaneous eigenstates to both the Hamiltonian and the reflection operator. Now, why do we do this? Well, because the reflection operator is easy to describe in K-space. And to see that, I'm going to show you something here, what this line defect does. This is one sublattice with a blue. The other sublattice is with a green. And now assume that you do a reflection around the line defect. You see that all of the blue atoms on one side go over to green atoms on the other side, and vice versa. So you're really just swapping the sublattices. And the way to represent swapping sublattices in K-space is just through the Pauli matrix sigma x. It's just swapping the A and B sublattice. So now we know that we have this commutation relation. And the eigenvalue equation of the Pauli matrix X is a trivial one. It just has symmetric and antisymmetric solutions. So your eigenstates can now be written as a symmetric and antisymmetric combination of the two sublattices. So that means that the graphene states can also be represented in this basis with symmetric and antisymmetric states. So, and also the, by the way, the symmetric states correspond to a pseudospin moving to the right. Antisymmetric corresponds to pseudospin to the left in our definition. So, now, why are we going through this exercise? Well, if you form the full Hamiltonian, which you can do by starting from the graphene and you make modifications that has to do with the line defect, you get a total Hamiltonian here that has defect sides, and you also have other interaction terms. I'm sorry. All right. So anyway, continuing this assumption, it actually turns out that the full Hamiltonian here commutes with a reflection operator, not just to the graphene, but to everything. So you have this whole identity here. Now, if you consider antisymmetric states have a node right at the line defect. Well, if it has a node, that means that the density there is 0. It's the modulus squared, essentially, of the wave function here, and the wave function is 0. So that means that there's no density here. That actually decouples the two sides. Because you decouple the sides, you get approximately 0 transmission through the antisymmetric states. The symmetric states, on the other hand, can just propagate straight through the line defect, as it turns out, with no problem. So this is really a perfect pseudospin filter that allows symmetric states and not antisymmetric states. Well, the transmission now that we did with quantum transport before, here is the one line of calculating the transmission that we did through quantum transport before. Well, take your graphene state, project it onto the symmetric state, which is the only one that transmits, take the modulus squared, and that's the exact same result that we had before. So this one little identity here we could have done from the beginning if you know the arguments that we used before. So I just wanted to demonstrate that because that's a really powerful, the physics in graphene here. You can also think of pseudospin measurements if you want. And the line from the line defect, you get the transmission probability as a function of the pseudospin as follows. Valley polarization, defined like this, really divided by the sum over the two, but it's actually 1 in this particular case. So the polarization is just the sign of the angle of incidence. So it's just plotted here, and here you just can see the pseudospins illustrating exactly that. In this case, for this particular angle, the pseudospin in one valley points to the right, that can go through, the other one points to the left, that's reflected. And if you have angle of incidence at the 90 instead of minus 90, it's reversed. Now the line defect could not only filter carriers in graphene, but also used for measuring. So if you send through a carrier, if it goes through, you have a high likelihood that it belongs to a particular valley, and if it reflects, it belongs to the other valley. So this is something that we published in PRB back in 2011, and this is really quite different from anything previously on valley information. All right, so moving on. So that was just the valley aspect, but there are many properties of this line defect coming out of the symmetry. I mentioned local magnetic moments before, and actually I'm not going to talk about that here. But the third one was about chemistry. So we have done first principles calculations, and you can see from the energy analysis that the binding energies are significant. So the binding here is actually using the dimers, where a lot of people use just single atoms when they calculate the binding, but the binding energies are so significant that it overcomes the dissociation energy of these diatomic molecules. And in fact, it's not shown here, but it even breaks the triple bond of N2. It weakens it. It doesn't completely break it. It weakens it from a triple bond down to a double bond. This is significant because the triple bond in nitrogen is just one of the strongest bonds that is known. So the fact that we can actually weaken that and potentially attack it with further chemistry could actually have a big impact if it's indeed possible to break the N2. But that remains to be seen. So anyway, with this we have calculated band structures if you periodically repeat these structures, and we have developed a tight binding model again, and the tight binding agrees really well with the density functional theory calculations. But of course now we start to have multiple options here. So my goal is that I don't like to study A, B, C, D, E. I prefer to make a general model that applies to everything if I can. So that was really the goal here. So I started to ask the question, what if we just have a general short-range scatter? How can we model that? One of the intriguing things is, can we have specular scattering? And actually, we can have specular scattering. By that I mean, when you reflect exactly like this, where the angle of reflection is the same as the angle of incidence, with a potential minus sign. But that we usually have in what's known as a specular limit, and that's when the wavelength is a lot larger than any barrier feature. Now, that's actually not satisfied in graphene. In graphene, we really can talk about two wavelengths. One is associated with where are we with respect to the values, and the other wavelength has to do with this microscopic wavelength that has to do with that the K points are not at the gamma point. So it creates this phase that I mentioned before, 0 and plus minus 120 degrees. However, even though the specular limit is not satisfied, we can actually still achieve it. And the way to achieve it is to look close closely by the Fermi level, because close to the Fermi level, this E goes towards 0, so this wavelength becomes very large. The scattering that has to do with this other wavelength, we can actually also beat if you make use of crystal momentum conservation along the structure. Now, there are some restrictions on that, so just to keep that in mind. Well, anyway, so now that we know that we could achieve specular scattering, we can create a general barrier model where we just assume an effective coupling across the barrier, and also potentials at the interfaces. So this is, in some sense, the simplest model. We can describe the semi-infinite graphene using self-energies and just solve that problem. And if we do that, again, calculate analytically, we find a transmission probability as a function of the angle of incidence. That's just the result here. It depends on the barrier coupling and the potential, and this is an asymmetry parameter, but most of the time we wouldn't have to worry about that. We have also verified this against tight binding calculation. So this is a simulated structure. So when we did the tight binding calculations, and we put in different types of barriers, and the blue dots is a tight binding, and the yellow line here is just what we get from our model. All right, so I'm not going to go into detail here. So how much time do I have?
About 5 more minutes.
Okay, so that's yes. So the idea here is that you can actually measure the transport through a barrier, even when you have no current through it. This is classically impossible. To measure something through a barrier, you must have some particles going through. Well, in the quantum world, you actually don't need that because there are really particles moving the whole time, and they are constantly probing the barrier and creating density oscillations around the barrier. And by studying the density undulations here, you can get information about the transport. So this is some more theory here. Maybe I should just show this for 5 seconds so it goes on to the video here so you can actually see this for yourself later if you're interested. All right, so the bottom line here is that we can calculate all of the densities, and at the end of the day we end up with a recipe where if you know the density undulations, we can estimate the parameters of the barrier and obtain the transmission probability. And again, our model, we just have verified it against some sample tight binding calculations. Actually, these tight binding calculations are in 3 different directions in graphene, and but they all fit really well with our model. Density undulations scale actually different from what you would expect from an isolated impurity. So no one has really shown this, but if you can create a barrier, you should see a different scaling behavior. So that's just something that has yet to be demonstrated. Moving on. So resonant tunneling. So this is conventional resonant tunneling. You get discrete states in energy. People have created resonant tunneling diodes that was mentioned this morning, and they have started to make their way into the commercial industry by now. Actually, these were proposed several decades ago. What we propose here instead is to use lateral transport. If you do lateral transport, resonant transport, you can backgate it. So you have the diode properties, but you can now backgate it. So you have this control to make it into a switch. Well, for all this to work, we need a barrier that is highly reflective. So resonant tunneling must have highly reflective barriers. Well, if you just decorate it with hydrogen or anything, you get a highly reflective barrier. This is translational symmetry in this direction. So I've plotted the transmission as a function of energy of the carrier and the quantum number along this translational symmetry. So you can see the transmission here is very small for the hydrogen case, and if undecorated line defect, it's large. So now what happens when we have 2 line defects in parallel? You get the resonances. Well, the resonances don't look like what we are traditionally accustomed to. They form these resonance bands. And in the extreme case, when you create the transmission probability goes to 0, then you are really talking about bound states. Bound states is a zigzag ribbon. So you see these resonances follow the band structure of zigzag ribbons. But the resonance band terminates. There's a dimensional crossover happening here. And because of that, you open up this gap. So just to demonstrate again, you can actually map all of the states onto the Dirac cone. So these are the states allowed by the boundary conditions formed by these 2 barriers. And most of them are 2D states mapped onto the Dirac cone. Some of the states leave, and they leave right at these critical points that form the dimensional crossover. So these states are 1D states, the rest are 2D states. The 1D states cannot carry any transport across here because they're localized in this direction. The group velocity in 1D states perpendicular to this is 0, identically equal to 0. That's why we open up this gap. So, all right, so that's my time, I think. I heard a little beep here. All right, so anyway, you can calculate the conductance, you get a clear gap, and you don't need to worry about so when you make nanotubes and ribbons, you're worried about the contact resistance. In this case, you don't need to worry about contact resistance because there are many, many, many channels. So there is no contact resistance at all here to be concerned about. All right, so with that, I thank you for your attention. And yes, so he asked about the Anderson localization in nanoribbons. I wouldn't say that the Anderson localization directly has to do with the gap, but rather the degradation of the transport properties. And the temperature dependence you see through variational, variable range hopping. So that's a manifestation of the Anderson localization. So without the Anderson localization, you wouldn't have the variable range hopping, and that's where you see the temperature dependence. What's that?
It's all consistent.
Yes.
So one question regarding this Valley transport.
Yes.
Because of great boundary.
Yes.
So have you looked at like the misorientation between the two graphene layers?
I haven't done that personally, but I believe other people have looked at it when you have the 2 layers of graphene. So I've only looked at this with a single layer. So that work was back in 2011. A lot of other people have published on 2 layers and misorientation.
All right. So let's thank the speaker.